Look up at the night sky and you see a single, brilliant point of light where a star resides. It feels like the natural order of things, a solitary sun ruling its domain. But what if that picture is a cosmic illusion, a simple-minded view of a far more complex and chaotic reality? Imagine for a moment that our familiar, steady sun was not alone. What if it had not one but 5 siblings, all bound together in an intricate gravitational dance, their light blending into a single, untwinkling beacon in the heavens? This isn't just a flight of fancy, it is the reality for countless stars, living in vast, complex families that defy our simple understanding of how solar systems work. We are about to embark on a journey into the heart of these cosmic wonders, specifically into the strange and turbulent world of sextuple star systems, where 6 suns share a single chaotic address. To call these systems families is an understatement. They are celestial ballets of unimaginable complexity, governed by physics that would seem like science fiction. The gravitational forces at play create environments of extreme chaos and bizarre stability, where planets, if they can form at all, would experience days with multiple sunrises and sunsets, and skies filled with a tapestry of light and shadow that would make our own world seem profoundly lonely. The very existence of these systems challenges everything we thought we knew about star and planet formation, pushing the boundaries of astrophysics and forcing us to reconsider what is possible in our universe. They are not mere curiosities, they are extreme laboratories testing the limits of cosmic architecture and hinting at possibilities for life in conditions we can barely comprehend. In this video, we will dive deep into 30 of the strangest discoveries scientists have made about these sextuple star systems. We will uncover mind-bending facts about their formation, explore the gravitational chaos that defines their existence, and ponder the incredible possibilities for planets that might call such a place home. From stellar orbits that resemble intricate clockwork to cosmic configurations that border on the impossible, each discovery reveals a new layer of complexity in our universe. So prepare to have your perception of the cosmos permanently altered as we count down 30 revelations that prove reality is far stranger and far more wonderful than we ever imagined. The journey into this family of 6 suns begins now. Our journey into the bizarre begins with a question so fundamental it challenges the very laws of physics. How can a system of 6 stars possibly hold itself together? For centuries, astronomers understood that even a simple system of 3 gravitationally bound bodies is inherently chaotic. This is the infamous 3-body problem, where predicting the long-term motions of just 3 stars is mathematically impossible. Their interactions are so complex that tiny, imperceptible changes in their starting positions can lead, over millions of years, to one star being violently ejected or a catastrophic collision. Apply this logic to 6 stars and the mind reels. The sheer gravitational turmoil should tear such a system apart in a cosmic blink of an eye. The first and perhaps most profound discovery about sextuple systems is that they not only exist but can achieve a strange, delicate, and enduring stability. The secret lies in their architecture. These are not 6 stars swirling in a single, frantic mosh pit. Instead, they are organized in what astrophysicists call a hierarchical structure. Think of it as a cosmic family tree written in gravity. At the smallest level, you have 2 stars locked in a tight, intimate orbit around each other, a binary pair. Another pair does the same nearby. These 2 stable binaries then become the dancing partners, circling each other at a much greater distance. This creates a stable quadruple system. Now take that entire complex quartet and have it orbit another close-knit binary pair, but at a distance so vast it makes the previous orbits look tiny. This nested Russian doll configuration is the key. The gravitational influence between the most widely separated pairs is weak enough that they behave almost as single objects, effectively simplifying the maddening six-body problem into a series of more manageable two-body interactions. It's a brilliant cosmic workaround, a loophole in the laws of physics that allows for stability through separation. This theoretical framework was proven possible not through direct observation alone, but through the power of computer simulations. By modeling millions of possible orbital configurations over billions of virtual years, scientists watched as most hypothetical sextuple systems tore themselves to pieces. But a rare few, those with just the right ratios of distance and mass, persisted. They revealed a clockwork of orbital periods, the innermost pairs completing their dance in a matter of days, the intermediate pairs taking years, and the outermost partners requiring centuries or even millennia to complete a single loop. This discovery fundamentally rewrote our understanding of celestial mechanics, proving that the universe can build structures of astonishing complexity that endure for eons, not through simplicity, but through an exquisite and layered order. But knowing that such systems are theoretically possible is one thing. Finding one shining brightly in our own cosmic backyard is another entirely. And that brings us to our second astonishing discovery. One of the most famous and recognizable stars in the entire night sky is in fact a secret sextuple system. For millennia, observers have looked up at the constellation Gemini, the twins, and seen the brilliant star Castor, often thinking of it as a single point of light. But Castor has been keeping a spectacular secret. Modern astronomy has ripped away that illusion, revealing that Castor is not one star, not even two, but a breathtaking family of 6 suns all bound together. This isn't some faint, distant speck at the edge of the observable universe. It is our nearest known sextuple neighbor, located just 51 light-years away. That distance, in galactic terms, is practically next door, making Castor an invaluable natural laboratory for studying the intricate physics of multiple star systems up close. The unraveling of Castor's true nature is a story of technological progress. Initially, through a telescope, Castor was resolved into 2 stars, a bright pair now known as Castor A and Castor B, orbiting each other over a period of several centuries. That alone was a remarkable find, but the story deepened with the advent of spectroscopy, the technique of splitting starlight into its constituent colors to reveal the fingerprints of chemical elements. When astronomers analyzed the light from what they thought was a single star, Castor A, they found something perplexing. The spectral lines were not steady. They shifted back and forth, a clear sign that Castor A itself was not a single object, but a pair of stars orbiting so closely that not even the most powerful telescopes of the time could separate them. The same phenomenon was discovered for Castor B, so what appeared as 2 stars was actually 2 tight binary pairs, but the surprises didn't end there. A much fainter star, catalogued as Castor C, was found loitering nearby. Spectroscopic analysis revealed that Castor C, too, is not a single star but a 3rd binary pair, a duo of small, dim red dwarfs locked in a frantic orbital embrace. The full picture that emerges is one of staggering complexity. The Castor system is a perfect example of the hierarchical stability we just discussed. At its heart are 3 binary pairs, Castor R and AB, Castor Bar and BB, and Castor Car and CB. The first 2 bright pairs, A and B, orbit each other on a timescale of about 450 years. This quadruple system is then gravitationally tied to the 3rd, fainter pair, Castor C, which takes tens of thousands of years to complete a single grand orbit around the central quartet. This configuration makes Castor a textbook case of cosmic architecture, a real-world confirmation of the theoretical models. Its proximity allows astronomers to measure the masses, temperatures, and orbital characteristics of these stars with unprecedented precision, providing a crucial benchmark for understanding how such complex systems form and evolve. To look at the bright point of light that is Castor and know that you are seeing the combined glow of 6 individual stars, a cosmic dance playing out on timescales from days to millennia, is to truly grasp that the universe is far more wondrous and intricate than it appears to the naked eye. All of this celestial architecture leads to a question that fires the imagination. Could planets actually exist in such a turbulent environment? The idea of a world with 6 suns in its sky seems like pure fantasy, a setting for an epic science fiction saga. Yet, one of the most mind-bending discoveries about these systems is that planets are not only possible, but some may even exist in stable orbits, creating environments where the concept of habitable takes on a whole new meaning. The challenges for planet formation and survival here are unsurprisingly monumental. Imagine the process of planet birth, which in our own solar system involved dust grains gently sticking together in a quiet, stable disk around a single infant sun. Now place that process inside a sextuple system. The gravitational tides from multiple young stars would constantly stir the protoplanetary disk, creating violent collisions that could shatter forming planets before they even had a chance to grow. The environment would be one of constant gravitational bullying, where a planet's path could be violently altered, sending it careening into a star or being flung out of the system entirely into the dark interstellar void. Even if a planet miraculously forms and finds a stable orbit, its existence would be anything but peaceful. The light and heat it receives would fluctuate wildly as different stars rise and set in its sky. There would be periods of multiple overlapping days and other times of profound darkness when all 6 suns are below the horizon. Surface temperatures could swing from scorching to freezing on timescales that could be days, years, or even centuries, depending on the complex orbital dances. This is not the gentle, consistent warmth of a single star that life on Earth enjoys. It is a roller coaster of stellar energy that would push any potential ecosystem to its absolute limits. Yet against all odds, astrophysics provides a path to stability. Just as the stars themselves achieve order through a hierarchical structure, planets can find safe harbors within the gravitational chaos. The key lies in orbiting the system's center of mass, the balancing point of the entire stellar family, at a very great distance. If a planet is far enough away, the complex tug of war between the individual stars averages out, and the entire sextuple system can act as a single gravitational point source. This creates a single, broad habitable zone, a region where temperatures could be right for liquid water to exist on a planet's surface. Furthermore, there are specific gravitational sweet spots known as Lagrange points. In any two-body system, these are positions where a smaller object, like a planet, can maintain a stable orbit relative to the 2 larger bodies. In a sextuple system, the most stable option for a planet would likely be orbiting one of the tight binary pairs, but far enough out that it's effectively orbiting their combined center of mass. Scientists have run sophisticated simulations and found that in certain configurations, these orbits can remain stable for billions of years, long enough for life to potentially emerge and evolve. This discovery fundamentally redefines the search for extraterrestrial life. For decades, the hunt has focused on Earth-like planets around single, sun-like stars. But if planets can thrive in the extreme environments of sextuple systems, it means the real estate for life in our galaxy is vastly larger and more diverse than we ever dreamed. Life, if it exists in such a place, would have to be incredibly resilient, perhaps hibernating during long cold spells and flourishing during brief, warm summers when several suns shine. The very possibility forces us to expand our imagination about what life could be and where we might eventually find it, turning these chaotic families of stars into some of the most compelling targets for future exploration. Now, while the hierarchical dance of these stars provides a framework for long-term stability, that stability is a distant mathematical average. Up close, in the tight orbits between the individual stars, the reality is one of gravitational violence that can warp and tear at the stars themselves. This brings us to our next astonishing discovery, the power of tidal forces. We're all familiar with the tides on Earth, the gentle rise and fall of the ocean caused by the moon's gravity. But in a sextuple system, tidal forces are not gentle. They are titanic, destructive powers that can sculpt stars, rip away their atmospheres, and trigger cosmic explosions. The key to understanding this lies in a concept called the Roche-lobe. Picture a star not as a perfect, isolated sphere, but as a fluid ball of plasma held together by its own gravity. Now imagine another star orbiting very close to it. Each star exists within its own gravitational domain, its own bubble of influence. The Roche-lobe is the teardrop-shaped boundary of that domain. As two stars in a tight binary pair whirl around each other, their Roche-lobes touch. If one star begins to swell, as stars do when they age, its outer layers can cross that invisible boundary. The moment that material passes the point of no return, it is no longer bound to its parent star. Instead, it falls under the dominant gravitational pull of the companion, streaming across the space between them in a vast river of superheated gas. This is not a slow leak, it's a stellar hemorrhage. In a sextuple system, this process becomes exponentially more complex and violent. You don't just have one pair of stars interacting, you have multiple pairs, and these pairs themselves interact. A star transferring mass to its partner can suddenly have its own orbit altered by the gravitational tug from another binary pair circling nearby. This can compress the orbit further, accelerating the mass transfer into a torrent. The infalling gas doesn't land gently. It spirals down at incredible speeds, forming a searingly hot accretion disk around the receiving star. The friction within this disk can heat the material to millions of degrees, causing it to glow with intense X-rays. But the most dramatic effects occur when the instability reaches a breaking point. The sudden dumping of a huge amount of fuel onto a star, especially a dense white dwarf or a neutron star within one of these binaries, can trigger a runaway thermonuclear reaction. The result is a cataclysmic stellar flare, a nova, or even a supernova explosion that can outshine the combined light of all the other stars in the system. Imagine the scene. A stable, multi-sun system suddenly illuminated by a brilliant new temporary sun, a flash of destruction born from the intimate gravitational embrace of its own stellar family. These tidal interactions can also lead to a slower, more gruesome fate, stellar cannibalism. In an extremely close binary, the stronger gravitational field of a denser star can, over time, literally strip the outer layers from its larger but more diffuse companion. The victim star is slowly peeled apart, its material siphoned away until only its dense core remains. In a sextuple system, the gravitational perturbations from the other stars can push a binary pair into an orbit tight enough for this process to begin, turning a stable relationship into a predatory one. The changes in brightness from these events are not subtle. A system might appear constant for centuries, then suddenly flare to many times its normal luminosity as a mass transfer event begins, only to fade again as the fuel is exhausted. For an observer, the light from such a system would be a flickering, unpredictable beacon, a direct window into the real-time destruction and rebirth happening within. This proves that the stability of these systems is a dynamic, often violent, equilibrium, where the serene clockwork of orbits masks a reality of continuous stellar transformation and cosmic drama. This constant gravitational tug of war within the system's tightest orbits leads to one of the most dramatic and visually striking phenomena in all of astronomy, the creation of stellar vampires. We've seen how material can flow across the boundary between two closely orbiting stars, but this process can become a full-scale act of cosmic predation. In a tight binary pair, if one star is more massive and has evolved faster, it might collapse into a super-dense remnant like a white dwarf. Its powerful gravity then begins to pull the very atmosphere off its still living companion. This isn't a gentle transfer, it's a siphon, a relentless drain that can strip a star of its outer layers over millions of years. the stolen hydrogen gas doesn't just vanish. It spirals down onto the surface of the vampire star, piling up under intense heat and pressure. But what happens when both stars in the binary are still in the main phase of their lives and one begins to steal from the other? This is where things get truly strange and leads to a cosmic paradox: stars that defy their age. In a typical star cluster, all stars are born at roughly the same time. The most massive ones burn through their fuel quickly, becoming red giants and then dying, while the lower mass stars remain, burning steadily for billions of years. You can therefore tell the age of a cluster by its most massive remaining stars. However, astronomers began noticing stars in ancient clusters that were far too hot, massive, and blue to still be there. They stood out like youthful athletes in a retirement home. These anomalies were dubbed blue stragglers, and for decades their existence was a major puzzle. How could a star appear billions of years younger than its siblings? The answer, we now know, is mass transfer. In a close binary system within a cluster, or with even greater complexity within a sextuple system, one star can swell up as it ages. As it expands, its outer layers become gravitationally vulnerable to its companion. The smaller, younger star then feeds on this material, pulling hydrogen-rich fuel onto its surface. This influx of new fuel does something remarkable. It rejuvenates the star. The added mass increases the pressure and temperature in its core, reigniting nuclear fusion with a new intensity. The star becomes hotter, brighter, and bluer, effectively resetting its evolutionary clock. It now looks and behaves like a much younger star, even though it was born at the same time as its neighbors. It has become a blue straggler, a cosmic vampire that has stolen not just material, but youth itself. In a sextuple system, the gravitational nudges from the other stellar pairs can force binary stars into the close orbits necessary for this vampiric process to begin, making these systems fertile ground for creating such stellar anomalies. Observing a blue straggler in a system like Castor would be a direct confirmation of this violent, life-extending process happening in real time. The constant gravitational interactions and the potential for mass transfer we just explored are not just theoretical. They have a direct, observable consequence that has baffled and fascinated astronomers for centuries: wild, unpredictable changes in brightness. While a single star like our Sun shines with a remarkable constancy, the combined light from a sextuple system can flicker, flare, and dim in patterns of mind-bending complexity. This isn't just random noise, it's a cosmic symphony of light, with each variation telling a specific story about the stars causing it. The primary driver of these changes is the simple geometry of eclipses. In a system with multiple pairs of stars orbiting in different planes, the chances of one star passing in front of another from our vantage point are incredibly high. But this is far from the simple, periodic dimming we see in a typical eclipsing binary. Imagine trying to predict the pattern of shadows in a room where 6 different light bulbs are swinging from the ceiling on separate, crisscrossing paths at different speeds. One moment, a bright, hot star might be partially hidden by a cooler, larger companion, causing a deep, sharp dip in brightness. Hours or days later, 2 stars from a completely different pair might graze each other in the sky, creating a subtle V-shaped dimming. Then, just as the light seems to stabilize, a third pair could align in such a way that one star reflects the light of another toward us, causing a tiny, brief flare. The combined light curve, the graph of brightness over time, becomes an erratic scribble, a seemingly chaotic mess that holds the key to unlocking the system's deepest secrets. Deciphering this light curve is one of the most demanding challenges in observational astronomy, a painstaking process akin to solving a multi-layered puzzle with pieces that are constantly moving. The first and most crucial tool for this is the transit method, but applied on a scale of staggering intricacy. By meticulously measuring the precise depth, duration, and shape of each and every dip in brightness, astronomers can reverse engineer the physical characteristics of the stars involved. A deep, long eclipse suggests a large star is passing in front of a bright one. A short, sharp dip might mean a small, dense star is transiting quickly. The shape of the dip's edges can even reveal information about the transiting star's atmosphere. But in a sextuple system, these individual eclipses are superimposed on top of one another. A dip from one binary pair might be interrupted by a dip from another, creating a complex blended signal that requires powerful computer algorithms to untangle. Astronomers create sophisticated mathematical models of the entire system, simulating the light from all 6 stars and their orbits. They then tweak the model's parameters, the sizes of the stars, their orbital periods, the tilt of their orbital planes, until the simulated light curve matches the observed one perfectly. It's a monumental task of fitting a theoretical model to an immensely complicated reality, and it can take years of observation and computation to achieve a reliable solution. Beyond simple eclipses, another fascinating phenomenon comes into play: reflection effects. In a very close binary pair, the stars are so near to each other that one star's light can significantly heat the facing hemisphere of its companion. The heated side then glows brighter, much like the moon is illuminated by the sun. As the stars orbit, the amount of heated surface visible from Earth changes, causing a smooth, sinusoidal variation in brightness that peaks when the heated side is fully facing us. In a sextuple system, you could have multiple reflection effects happening simultaneously within different binary pairs, each with its own period, adding another set of overlapping waves to the already complex light curve. Furthermore, if mass transfer is occurring, the hot accretion disk formed around the receiving star can be an incredibly luminous object, and its brightness can vary as the flow of material changes due to gravitational perturbations from the other stars in the system. This adds a layer of stochastic or random flickering on top of the periodic eclipses and reflections, making the light curve even more difficult to interpret. Each of these tiny variations is a data point, a clue that helps astronomers build a precise map of the entire system, determining not just where the stars are, but also their temperatures, their sizes, and even their approximate shapes, which can be distorted by their immense gravitational pulls. The flickering beacon of a sextuple star system, once seen as a mere curiosity, is now understood as a rich and detailed broadcast, transmitting the secrets of its chaotic and beautiful internal dance across the light years. Yet, even with our most advanced tools, discovering a system with 6 gravitationally bound stars is like finding a specific, intricately crafted snowflake in a blizzard. They are exceptionally rare, representing a tiny fraction of a percent of all known star systems. This rarity isn't a coincidence, it's a direct consequence of the immense challenge of assembling and maintaining such a complex gravitational arrangement. The process of star formation is a turbulent affair. A vast cloud of gas and dust collapses under its own gravity, but it's also spinning. This spin flattens the cloud into a disk which can fragment. Sometimes these fragments form pairs or triplets, but for a sextuple system to arise, the initial conditions must be just right. The cloud must have the perfect amount of spin and density to fragment into multiple stable pairs that are then captured into a grand hierarchical orbit. More often than not, the gravitational interactions during this chaotic birth period are too violent, flinging stars away before they can settle into a stable multi-generational family. A nascent sextuple system is a fragile house of cards being built in a hurricane. Only the most perfectly balanced configurations survive. This extreme scarcity means that finding them requires a combination of patience, precision, and brilliant detective work. Astronomers cannot simply point a telescope at the sky and see 6 stars orbiting each other. The vast distances and tight inner orbits make directly resolving most of them impossible. Instead, they rely on indirect methods that reveal the system's hidden architecture through subtle clues. one of the most powerful techniques is radial velocity measurement. This method relies on the Doppler effect, the same principle that causes a siren's pitch to change as it races past you. As a star moves in its orbit, it will periodically be pulled toward us and then away from us by its unseen companion. When it moves toward us, the light waves are compressed, shifting its light slightly toward the blue end of the spectrum. When it moves away, the light is stretched, shifting it toward red. By taking thousands of precise spectra of a star over years or even decades, astronomers can detect this rhythmic back and forth wobble in its light. For a single binary star, the radial velocity graph is a smooth, predictable wave. But for a star in a sextuple system, the story is vastly more complex. The primary wobble from one binary partner is itself wobbling due to the gravitational influence of a second binary pair, which in turn is being tugged by a third. The resulting radial velocity curve is not a simple wave, but a tangled superposition of multiple waves, each with its own period and amplitude. Untangling this signal is a monumental task requiring sophisticated computer models to fit the data and confirm that the wobbles can only be explained by the presence of 5 unseen stellar companions. Another crucial technique is astrometry, the ancient science of measuring the precise positions of stars in the sky. With modern instruments like the Gaia Space Observatory, this has been elevated to an art of unbelievable accuracy. Gaia measures the positions of billions of stars with a precision equivalent to determining the diameter of a human hair from 1,000 kilometers away. It can detect the tiny, elliptical path a star traces across the sky as it is tugged by its companions. For a sextuple system, this proper motion isn't a smooth arc. It's a path with slight, periodic wiggles and deviations, the telltale signature of multiple gravitational influences perturbing its course through space. By combining the radial velocity data, which gives information about the star's motions toward and away from us, with the astrometric data, which maps their motion across the plane of the sky, astronomers can construct a three-dimensional map of the orbits. This powerful combination allows them to calculate the masses of the stars involved with remarkable precision, confirming that the unseen companions are indeed stars and not planets or brown dwarfs. Each new sextuple system discovered is therefore a testament to the ingenuity of modern astronomy, a puzzle solved not by a single observation, but by piecing together decades of painstaking data into a coherent picture of cosmic complexity. The chaotic environments where stars are born might seem like the least likely places to build a structure of delicate gravitational stability, but counterintuitively, it is within these cosmic pressure cookers that the seeds of sextuple systems are often sown. To understand why, we must leave behind the quiet solitude of our own solar system's origins and venture into the heart of a dense star cluster. Imagine a stellar nursery not as a serene, isolated cocoon, but as a sprawling, chaotic metropolis in its infancy. Thousands of young, brilliant stars are being born in close proximity, their gravitational fields crisscrossing and interacting in a frenzied ballet. In such a crowded neighborhood, close encounters are not just possible, they are inevitable. This constant gravitational jostling provides a powerful mechanism for building complex stellar families, a process known as dynamical capture. The theory is elegant in its simplicity. Let's say you have two simple binary systems that formed independently. In the vast, empty space between stars, these two pairs would likely never meet, destined to live out their lives in isolation. But place them both inside a dense, young cluster, and their fates become intertwined. As they drift through the crowded core, their paths may cross. During this close encounter, the complex gravitational dance between the four stars can result in an exchange of energy. Sometimes, this interaction is so violent that one or more stars are ejected at high speed, becoming runaway stars. But in other, rarer instances, the gravitational energy is redistributed in a way that binds the two binaries together. Instead of flying apart, they become gravitationally tied, forming a new, stable quadruple system. Now introduce a third binary pair into the mix. Another close encounter with this newly formed quartet could, through the same chaotic physics, capture it into an even wider orbit, culminating in the hierarchical sextuple system we observe. This process is essentially nature's way of building complex structures through gravitational accidents, turning random flybys into permanent celestial families. This dynamical capture theory offers a compelling explanation for why we might find these rare systems more frequently in or near the remnants of such clusters. While many clusters dissolve over billions of years as their stars drift apart, the gravitational signature of their dense origins can persist. A sextuple system discovered moving through space as a seemingly isolated group could be a relic, a surviving testament to a wild youth spent in a packed stellar environment. The system's very existence is a fossil record of the crowded conditions in which it was forged. This idea is bolstered by sophisticated N-body simulations, where physicists model the gravitational interactions of thousands of stars in a virtual cluster. These simulations consistently show that while the formation of a sextuple system is always a low probability event, its likelihood increases dramatically in regions of high stellar density. The numbers tell the story. The rate of close encounters scales with the square of the stellar density. Double the density of stars in a region, and you quadruple the probability of these complex gravitational interactions occurring. However, there is a fascinating counterpoint to this cluster-borne theory, one that adds another layer of mystery to the origins of these systems. What if a sextuple system forms not from a chaotic gravitational scramble, but from a single, unusually fertile cloud of gas and dust? This is the theory of primordial fragmentation. In this scenario, a single, massive, and rapidly rotating protostellar cloud doesn't just collapse into one or two cores. It undergoes a kind of gravitational instability that causes it to fragment into several distinct clumps simultaneously. These clumps, born as siblings from the same parent cloud, could then naturally settle into the hierarchical orbits we see, their initial positions and motions dictated by the intricate dynamics of the fragmentation process itself. This would mean the system is a true family, sharing a common origin from the start, rather than a group of strangers brought together by chance encounters. Distinguishing between these two origins, dynamical capture versus primordial fragmentation, is a major goal for astronomers. The key evidence often lies in the system's kinematics, its motion through the galaxy. A system born from dynamical capture in a cluster might retain a high peculiar velocity, a kind of gravitational kick imparted during its violent formation. It might also be found on a path that traces back to a known stellar stream or a dissolved cluster. A system formed from quiet, isolated fragmentation, on the other hand, would more likely share the calm, circular motion typical of stars in the galactic disk, showing no signs of a violent past. By carefully measuring the trajectories of known sextuple systems, scientists can begin to piece together their life stories, determining whether each one is a product of a frenzied cluster environment or a rare but more serene process of monolithic collapse. This investigation reveals that there may be multiple pathways to the same incredible destination, and that the universe, in its boundless creativity, can build complexity through both chaos and quiet order. Now, if you think untangling the complex orbits of these systems is a challenge, wait until you try to identify what the stars themselves are actually made of. This brings us to the spectral signatures of sextuple systems, a realm where starlight becomes a fantastically complicated puzzle. Each star has its own unique chemical fingerprint, a barcode of dark absorption lines and bright emission lines imprinted on its spectrum. But when you point a telescope at a sextuple system, you're not collecting the light from one star, you're gathering a blended beam from all six simultaneously. The resulting spectrum is a chaotic superposition, a tangled web of overlapping lines where the signature of a hot, massive star is smeared together with the distinct pattern of a cool, elderly red dwarf. It's like trying to identify 6 different people speaking at once in a crowded room by listening to a single, blended recording. The complexity doesn't end with simple blending. Because the stars are in constant motion, their light is subject to the Doppler effect, causing their spectral lines to rhythmically shift back and forth. But here's the twist: each binary pair has its own orbital period. The lines from the stars in the tightest, fastest orbiting pair will be shifting on a timescale of days, creating a rapid wobble in the combined spectrum. Meanwhile, the lines from a wider binary will be shifting over a period of months or years, creating a much slower underlying drift. And the spectral lines from the entire system's slow, grand orbit could be shifting over centuries. This means that at any given moment, the position of a particular ion or hydrogen line in the spectrum is not a single, sharp mark, but a blurred smudge representing the average position of that line from all 6 stars, each Doppler shifted by a different amount. Trying to make sense of this spectral cacophony with traditional methods is utterly hopeless. It requires a computational approach of immense sophistication. The solution lies in a technique known as spectral disentanglement. This isn't a simple filtering process, it's an act of computational archaeology. Astronomers take not one, but dozens or even hundreds of high-resolution spectra of the system over time, capturing the stars in different orbital configurations. They then feed this vast dataset into powerful algorithms that are essentially given a model of the system. We think there are 3 binary pairs with these orbital periods. Now find the 6 individual spectra that, when combined and Doppler shifted according to these orbits over time, perfectly reproduce all of our observed data. The software performs a massive mathematical inversion, iterating through millions of possibilities to statistically separate the blended light. It's a painstaking process of subtraction and comparison, isolating the unique contribution of each stellar component. When successful, the result is breathtaking. From a single, messy signal, scientists can extract the pristine spectrum of each of the 6 stars, allowing them to determine their temperatures, surface gravities, chemical compositions, and even their rotational velocities with remarkable precision. This ability to peer into the heart of the chaos and identify each individual player is what transforms a mysterious flickering point of light into a detailed astrophysical laboratory. But the most dramatic outcome of this stellar interaction is what happens when the vampire is not a white dwarf, but a neutron star, or even more terrifyingly, a black hole. The material flowing from the donor star onto the surface of a neutron star doesn't just cause nova. It can build up until the entire star is crushed under its own weight, triggering a supernova explosion. In a sextuple system, the gravitational nudges from the other stellar pairs can influence the rate of this mass transfer, effectively acting as a cosmic timer. They could potentially delay the explosion by stabilizing the binary's orbit for a time, or they could hasten the cataclysm by forcing the stars closer together, accelerating the entire process. This means the very architecture of the system can dictate when one of its members will meet its violent end. Now, try to picture the immediate aftermath of such an explosion within a sextuple family. A supernova is one of the most energetic events in the universe, releasing in a few seconds more energy than our Sun will over its entire 10 billion-year lifetime. In our lonely galaxy, a supernova simply lights up the void. But in a sextuple system, that titanic blast wave of energy and matter slams directly into its 5 sibling stars. The star closest to the explosion would have its atmosphere brutally stripped away by the force of the impact. The sudden, asymmetric loss of mass from the exploding star, a process known as the supernova kick, would have profound and chaotic gravitational consequences. Imagine a table with 6 people holding onto a single, taut sheet. If one person is suddenly yanked violently away, the remaining 5 are sent tumbling. In the same way, the instant removal of a significant fraction of the system's mass sends a gravitational shock wave through the entire configuration. The delicate balance of the hierarchical orbits is shattered. The most likely result is a cosmic breakup of epic proportions. The immense energy of the supernova kick could easily provide enough velocity for one or more of the remaining stars to achieve escape velocity, flinging them out of the system entirely. These ejected stars would become hypervelocity runaways, streaking across the galaxy as permanent orphans, their origin story written in the frantic motions imparted by a sibling's death. The stars that remain would be left in a newly rearranged and likely highly unstable configuration. Their orbits would be radically altered, perhaps becoming wildly elliptical or even intersecting, setting the stage for further dramatic encounters, collisions, or even more supernova in a chain reaction of stellar destruction. The once stable clockwork becomes a broken mechanism, its pieces scattered and damaged. This revelation adds a profound layer of transience to these systems. Their magnificent stability is not necessarily forever. It can be irrevocably shattered in a single, blinding flash, a testament to the fact that even the most ordered structures in the cosmos are subject to the ultimate chaos of stellar death. But with every new discovery about their complex present-day mechanics, a deeper, more fundamental question looms. How did these intricate stellar families come to be in the first place? The origin of sextuple systems stands as one of the most tantalizing and unresolved puzzles in all of stellar astrophysics, with two compelling yet completely opposing theories vying for dominance. On one side, we have the theory of turbulent fragmentation, a story of a single spectacular birth. Imagine a colossal, monolithic cloud of gas and dust, far more massive than the one that formed our Sun. As this giant cloud begins to collapse under its own weight, it doesn't do so smoothly. Internal turbulence, rotation, and magnetic fields create violent, swirling eddies within the cloud, causing it to fragment not into one or two pieces, but into several distinct clumps simultaneously. In this scenario, all 6 stars are true siblings, born from the same parent cloud at roughly the same time. Their initial positions and motions are dictated by the chaotic but inherent dynamics of the cloud's collapse. The hierarchical structure we see today, the tight binaries orbiting each other at wider distances, could be a natural outcome of this process, a fossilized imprint of the cloud's initial density and spin. It's a top-down approach to building complexity, where a single entity shatters into a preordained stable family. The opposing theory, sequential capture, paints a vastly different picture, one of a slow, gravitational assembly over millions of years. Here, the stars are not siblings but strangers brought together by chance in a crowded stellar environment. Picture a dense, young star cluster, a celestial metropolis buzzing with youthful stellar activity. In such a crowded neighborhood, close encounters between stars are commonplace. The theory proposes that a simple binary system might, during a close flyby, gravitationally capture a third star, forming a triple. Later, another encounter could see that triple system capture another single star or even an entire binary pair, gradually building up the system's complexity step by step. This is a bottom-up process where random gravitational interactions sculpt a simple structure into an increasingly complex one. The hierarchical architecture is then not a birthright but a consequence of stability. The captured stars settle into the widest, most stable orbits to ensure the system's long-term survival, while the original tight binaries remain intact at the heart of the system. Each new addition is a testament to a violent past, a relic of a close call that resulted in a permanent bond rather than a destructive ejection. The debate between these two theories is far from academic. It strikes at the heart of how we understand star formation and the evolution of stellar populations. The evidence is maddeningly ambiguous. Proponents of turbulent fragmentation point to the remarkable fact that these systems exist at all. For sequential capture to work, the conditions have to be just right: a dense cluster environment and a series of gentle enough encounters to bind stars together without tearing the nascent system apart. The odds of building a stable sextuple system through a series of random captures, they argue, seem astronomically low. The clean, hierarchical order we observe looks more like the product of a single, coherent event than a piecemeal assembly. On the other hand, supporters of sequential capture argue that the sheer violence and chaos of a monolithic cloud collapsing and fragmenting directly into 6 distinct, stable pairs might be even less likely. They point to computer simulations of dense clusters that do, in fact, produce a small number of complex systems through dynamical interactions. Furthermore, if a sextuple system is found to be moving with a high velocity through the galaxy, or if its trajectory can be traced back to a now-dissolved star cluster, that will be strong circumstantial evidence for a capture origin, as such velocities are often imparted by gravitational slingshots during close encounters. The frustrating truth is that the formation of a sextuple system, whether by fragmentation or capture, is such a rare event that we simply don't have enough examples to draw a definitive conclusion. Each known system is a unique case study. Perhaps the universe is creative enough to employ both methods. Some sextuple systems may be born from quiet, monolithic collapse in relative isolation, while others are assembled through violent dynamics in stellar cities. Unraveling this mystery requires more than just observing the systems we know. It requires finding them in their infancy, still embedded within their natal clouds, to catch the formation process in the act. Until then, the origin of these magnificent stellar families remains an open question, a beautiful reminder that for all our knowledge, the cosmos still holds profound secrets about its own creative processes. Now, let's take this gravitational chaos to its ultimate extreme. We've seen how these systems can trigger stellar vampirism and even supernova, but the fallout from such cataclysms doesn't just vanish. It can leave behind the most bizarre and dense objects in the universe: neutron stars and black holes still trapped within the gravitational web of their family. And when that happens, a sextuple system can transform into something even more extraordinary: a gravitational wave factory. Gravitational waves are ripples in the very fabric of spacetime itself, first predicted by Einstein and finally detected a century later. They are generated by the most violent events in the cosmos, typically by massive objects accelerating dramatically, like 2 black holes spiraling inward and colliding. While the individual orbits of regular stars in a sextuple system are far too slow and weak to produce detectable waves, the story changes completely when compact objects enter the picture. Imagine a scenario where one of the tight binary pairs in the system consists of 2 neutron stars. These are the ultra-dense cores left behind after a supernova, each containing more mass than our Sun crushed into a sphere the size of a city. If these 2 stellar corpses are orbiting each other closely, they constantly lose energy by emitting gravitational waves. This energy loss is tiny, but over millions of years, it causes their orbit to slowly decay. They spiral closer and closer together in a slow, cosmic dance of death. In a simple, isolated binary, this process would eventually lead to a merger. But within a sextuple system, the gravitational influence of the other stars adds a fascinating twist. The gravitational tugs from the other stellar pairs can periodically perturb the neutron star binary's orbit. Sometimes these nudges can make the orbit more elliptical, which actually increases the strength of the gravitational waves emitted at the closest approach. At other times, the perturbations might temporarily stabilize the orbit, delaying the final collision. It's as if the other stars in the system are acting as cosmic conductors, subtly orchestrating the timing and intensity of the final space-time shattering event. This makes these systems prime candidates for future observatories like LISA, the Laser Interferometer Space Antenna, which is designed to detect low-frequency gravitational waves. The inspiral of two neutron stars or stellar mass black holes in a sextuple system would create a continuous humming signal in Lisa frequency band for years before they finally merge. What's more, the complex gravitational environment could potentially produce a unique signature. The waveform, the specific pattern of the ripples in space-time, would carry subtle imprints of the gravitational pulls from the other stars in the system. By analyzing these signals, scientists wouldn't just be learning about the merging objects. They could potentially map out the entire architecture of the sextuple system from the distortions in the gravitational waves alone, using the fabric of the universe itself as a diagnostic tool. This turns these stellar families into unparalleled natural laboratories, not just for studying stars, but for probing the fundamental nature of gravity. For all their intricate stability, the cosmic ballet of a sextuple system is a performance on a knife's edge. The gravitational harmony that allows 6 stars to dance together for eons is incredibly delicate, and astronomers have made the sobering discovery that for every successful system like Castor, there are likely many more that fail. These are the fragmented families, the almost sextuple systems that either never fully formed or are in the tragic process of dissolving before our eyes. Finding these disrupted systems is just as revealing as finding the stable ones, because they show us the violent forces that constantly work against such complex arrangements. The primary disruptor is, unsurprisingly, gravity itself, but not from within the system. The greatest threat comes from outside, from chance encounters with other stars, or even more powerfully, with giant molecular clouds. Our galaxy is not an empty void. It's a crowded place where stars drift through spiral arms brimming with immense clouds of gas and dust. As a sextuple system orbits the galactic center over hundreds of millions of years, its path will inevitably bring it close to one of these colossal structures. A giant molecular cloud can contain the mass of 1 million suns, and its gravitational pull is immense. When the system passes nearby, the cloud's gravity doesn't pull on all 6 stars equally. It tugs more strongly on the star that happens to be closest to it at that moment. This differential pull sends a gravitational shock wave through the entire system. The effect is like throwing a rock into a perfectly still pond. The serene surface is shattered by ripples. In celestial terms, these ripples perturb the orbits, particularly the fragile, wide orbits that bind the outermost binary pairs to the inner core. A single close passage can stretch these already vast orbits, making them more elliptical and unstable. If the encounter is very close, it can inject enough energy into one of the stars to give it escape velocity, ejecting it from the family forever. This process of stellar ejection is a cosmic reality show of the most brutal kind. The star that is cast out doesn't just drift away slowly, it is flung out at tremendous speed, becoming what astronomers call a runaway star. These stellar orphans streak across the galaxy, their high velocity a permanent scar from the violent gravitational encounter that expelled them. Meanwhile, the system left behind is wounded and unbalanced. The sudden loss of a member means the delicate gravitational accounting that held everything together no longer adds up. The remaining stars are left in new, unpredictable orbits that often lead to further instability. Sometimes the system breaks down completely, dissolving into 2 or 3 separate, simpler groups that go their own ways. In other cases, the system might stabilize into a new, less complex configuration, perhaps a stable quintuple or 2 separate binaries, but the grand sextuple architecture is gone forever. These dissolving systems are the ghosts of what might have been, their frayed gravitational bonds telling a story of a close call with a galactic giant. Observing these failures is a challenging task, as they are by their nature transient and hard to identify. The key evidence often lies in the motions of the stars. Astronomers using precise data from observatories like Gaia can sometimes trace the paths of runaway stars backward through space. In a few remarkable cases, these paths can be traced right back to a known star cluster or a multiple system, like finding the source of a river by following a single droplet upstream. When they find a high-velocity star whose trajectory intersects with a disrupted system, it provides compelling evidence for a past ejection event. Similarly, they might find a group of stars that are moving together through space but with velocities and orbits that are clearly not bound in a stable hierarchy. The stars might be drifting apart at a slow but measurable rate, like a family gradually dispersing after a shared tragedy. These are systems caught in the act of dissolution, offering a real-time glimpse into the destructive forces that shape the galactic population of stars. The discovery of these failed systems adds a crucial layer of drama to our understanding of cosmic evolution, reminding us that the universe is not only a place of creation but also of dissolution, where even the most beautiful and complex structures are subject to the relentless pull of external forces. And just when we thought the stellar dynamics couldn't get more extreme, we turn our gaze from the stars themselves to the cosmic construction zones that surround them, the swirling disks of dust and debris. In a solitary system like our own, a protoplanetary disk is a relatively serene environment, a flat, rotating pancake of material where dust grains can gently collide and stick together, eventually building planets over millions of years of quiet accretion. But place such a disk within the gravitational maelstrom of a sextuple system, and that serene construction site becomes a chaotic war zone. The 14th astonishing discovery is that these systems can indeed host complex, often wildly distorted, disks of material, but their fate is dictated by the relentless gravitational bullying from not one but 5 other suns. These aren't the smooth, orderly rings we see around young stars. They are dynamically sculpted, warped, and truncated into bizarre shapes that reveal the invisible hand of gravity at work. The primary mechanism at play is gravitational truncation. Each tight binary pair acts as a gravitational vacuum cleaner within its immediate vicinity. The space around them is a region of instability. Any dust grain or small planetesimal that ventures too close will have its orbit violently perturbed, either being flung out of the system entirely or sent on a collision course with one of the stars. This effectively carves out a large, empty cavity around each binary pair. Now imagine you have 3 such binary pairs, each clearing out its own territory. The remaining material is forced into a series of rings and arcs at very specific, stable distances, often far from the central stars, orbiting the entire system's center of mass. The resulting structure is not a single, continuous disk, but a patchwork of disjointed belts, like separate construction sites isolated from one another by vast gravitational no-man's lands. The gravitational influence doesn't stop at carving out spaces. It also stirs up the material within these belts. The periodic tugs from the other stellar pairs as they complete their orbits act like a constant drumbeat of disturbance. This prevents the dust and ice particles from settling into a calm, thin plane. Instead, the disk becomes puffed up and dynamically hot, meaning the particles are on highly energetic crossing orbits. In such an environment, gentle collisions that lead to growth are rare. Instead, particles are more likely to smash into each other at high speeds, shattering each other back into fine dust. This makes the crucial first steps of planet formation, the growth from dust grain to pebble to planetesimal, an incredibly difficult, almost Sisyphean task. The consequences of this constant stirring are dramatic and violent. One of the most direct results is a perpetual, heavy comet bombardment for any fledgling planets that do manage to form. In our solar system, the Oort cloud is a distant, frozen reservoir of comets that only occasionally gets perturbed, sending a comet inward on a long-period orbit. In a sextuple system, the gravitational perturbations are constant and powerful. The dusty debris belts are continuously being shaken, flinging countless comets and asteroids out of their stable orbits and sending them careening on chaotic paths through the inner regions of the system. For a young planet, this would mean an era of bombardment so intense it would make the late heavy bombardment that pockmarked the early moon look like a light drizzle. The planetary surface would be relentlessly pummeled, its atmosphere repeatedly stripped away, and any nascent life would be snuffed out before it could even begin. This creates a profound paradox. While a stable orbit for a planet might exist in the broad, averaged-out habitable zone, the actual environment within that zone could be so hostile due to constant impacts that it becomes utterly uninhabitable. Observational evidence for these warped disks comes from the powerful infrared eyes of space telescopes. As dust grains are heated by the starlight, they re-radiate that energy as infrared light. By mapping the infrared glow around a sextuple system, astronomers can reconstruct the distribution of this dust. In several cases, the resulting images are not smooth or symmetrical. They show lopsided, clumpy structures with bright arcs and sharp edges that are the undeniable fingerprints of gravitational sculpting. In one hypothetical model, a disk might appear as a narrow ring at a great distance, but with a pronounced gap on one side, a clear sign that one of the wider orbiting binary pairs periodically sweeps through that region, clearing it out like a celestial plow. In another scenario, the dust might be concentrated at the gravitational Lagrange points, the stable points ahead of and behind a star in its orbit, creating glowing clumps that lead and trail the star like cosmic attendants. Each of these distorted shapes is a frozen snapshot of the gravitational forces at play, a direct readout of the complex orbital dance that would otherwise be invisible. Studying these dusty wrecks allows astrophysicists to not only understand the violent conditions for planet formation, but also to precisely measure the masses and orbits of the stars themselves, using the dust as a tracer for the invisible gravitational field that confines it. Now consider the astronomer's classic tool for understanding a star, its light split into a spectrum that reveals its chemical makeup. This cosmic fingerprint is supposed to tell us about the star's birth, its age, and the pristine cloud of gas from which it formed. But within the intimate confines of a sextuple system, these fingerprints can become smudged, forged, and altogether bizarre. Discovery 15 reveals that these stellar families can harbor members with wildly anomalous chemical compositions, stars whose surfaces are polluted with elements that have no business being there, creating cosmic imposters that defy our standard classification schemes. The culprit, once again, is the extraordinary process of mass transfer. We've seen how one star can act as a vampire, stealing the outer layers of its companion. But what exactly is it stealing? It's not just generic hydrogen fuel. A star's atmosphere can become enriched with specific elements forged deep in its core through nuclear fusion. In a typical, isolated star, these heavier elements remain locked in the interior, hidden from view. However, when a star in a close binary swells into a red giant, its outer atmosphere becomes bloated and tenuous. If it has a nearby companion, that companion can begin to siphon off this enriched material. Imagine a scenario where the donor star has been fusing hydrogen into helium, and then helium into carbon and oxygen in its core. When its outer layers are transferred onto the surface of the receiving star, they deposit a layer of helium, carbon, and oxygen onto what was previously a pristine, hydrogen-rich surface. The receiving star's spectrum is suddenly transformed. It now exhibits the strong spectral signatures of these elements, making it look like a star that is far more evolved than it actually is. It becomes a blue straggler not just in temperature but in its apparent chemistry, a youthful-looking star wearing the atmospheric makeup of an elderly giant. This chemical pollution can create stars of a type that simply shouldn't exist in nature. Astronomers might observe a star that has the surface temperature and brightness of a main sequence star, yet its spectrum shows an inexplicable abundance of carbon or a severe depletion of hydrogen. In isolation, this would be a profound mystery, but in the context of a sextuple system, it becomes a telltale clue. a smoking gun that points to a past episode of stellar cannibalism. The most dramatic examples involve elements like barium or technetium. Barium is a heavy element that is normally produced deep within stars and during supernova explosions. To find a star with a barium-rich atmosphere but no other signs of old age suggests it didn't make the barium itself. It acquired it from a neighbor that has since evolved and died, transferring its chemically enriched material in a final cosmic bequest. Technetium is even more telling, as it is a radioactive element with a short half-life. Its presence in a star's spectrum is undeniable proof of very recent nuclear activity, either within the star itself, which would mean it's a giant, or on its surface, material freshly deposited from a companion's nuclear burning shell. Unraveling these chemical mysteries requires the most sophisticated spectral analysis. As we discussed, disentangling the light of 6 stars is a monumental task, but when scientists succeed, the individual spectra can reveal astonishing stories. One star in the system might show a completely normal composition for its mass and age, while its tight binary partner displays a bizarre overabundance of lithium or a strange ratio of carbon to nitrogen. These anomalies are not random. They follow predictable patterns based on which layers of the donor star were stripped away. By comparing the chemical signatures of the stars in a pair, astrophysicists can effectively perform a stellar autopsy, determining the mass and evolutionary state of the donor star before the transfer event began. This turns the entire sextuple system into a detailed historical record, its stars' atmospheres acting as living archives that document the violent interactions that have shaped their lives over billions of years. But even these complex orbital dances can hide an invisible, slow-burning fuse, a gravitational time bomb that can take thousands or even millions of years to detonate. This brings us to one of the most subtle and profound effects in all of celestial mechanics, a phenomenon known as the Kozai-Lidov mechanism. At its heart, this is a gravitational conversation between orbits. In a simple, isolated binary system, the orbit of one star around the other is fixed. Its shape or eccentricity and its tilt or inclination remain constant over time. But place that binary system within the gravitational sphere of influence of a distant third object, like one of the other pairs in a sextuple system, and everything changes. The distant perturber exerts a gentle but persistent torque on the inner binary, a kind of continuous gravitational nudge that slowly but surely alters its path through space. The result is a spectacular, long-term oscillation. Over timescales that can span tens of thousands of years, the Kozai-Lidov mechanism causes the eccentricity of the inner binary's orbit to swing wildly from nearly circular to extremely elongated, like a stretched rubber band, and then back again. As the orbit becomes more eccentric, it also changes its tilt relative to the plane of the wider orbit. This isn't a random change, it's a precise, predictable trade-off governed by the conservation of angular momentum. When the orbit is most circular, its inclination is at a minimum. As the eccentricity grows to its maximum, the orbit tilts over dramatically. Then the process reverses. This cycle repeats over and over, a slow, cosmic pendulum swinging between round and skinny, flat and tilted. For the stars trapped in this gravitational waltz, the consequences can be catastrophic. Imagine 2 stars orbiting each other in a comfortable, nearly circular path, always maintaining a safe distance. As the Kozai-Lidov cycle kicks in, their orbit begins to stretch. At its most eccentric, the stars spend most of their time far apart, but at the point of closest approach, known as periastron, they whip past each other at terrifyingly high speeds, separated by a mere fraction of their usual distance. This periodic close passage dramatically increases the risk of a tidal catastrophe. The immense gravitational forces at periastron can strip material from their atmospheres, trigger massive flares, or severely distort their shapes. In the most extreme cases, if the orbit is driven to become eccentric enough, the stars can pass so close that they actually graze each other, leading to a partial or even total merger. Two stars would coalesce into a single, new, and more massive star, fundamentally altering the architecture of the entire system in a single, violent event. What makes the Kozylidov mechanism so insidious is its timescale. It operates not over human lifetimes, nor even over the span of civilizations, but over epochs. From our perspective, the orbits of the stars in a system like Castor might appear perfectly stable. It is only through sophisticated computer modeling, projecting their motions millions of years into the future and the past, that the full scope of this cyclical drama is revealed. In a sextuple system, the potential for these interactions is magnified. You don't just have one tertiary perturber, you have multiple pairs, each capable of exerting this subtle influence on the others. The Kozylidov effect could be operating simultaneously on different binaries within the same system, each on its own multi-millennial clock, creating a layered tapestry of gravitational evolution where the fate of individual stars is being slowly, inexorably shaped by the distant pull of their stellar relatives. It is a powerful reminder that stability in the cosmos is often a dynamic and temporary state, and that the calm we observe today can be the prelude to a distant but inevitable storm. Now, after grappling with the profound physics of stellar death and gravitational waves, we arrive at a discovery that brings a touch of bureaucratic comedy to the cosmic chaos, the mind-bending challenge of simply naming the stars in these systems. While the universe arranges them in a beautiful hierarchical dance, astronomers have had to devise an equally complex and at times bewildering naming convention to keep track of who's who. It's a system that looks more like a complex password than a stellar designation, but every uppercase letter, lowercase letter, and numerical suffix tells a precise story about the orbital relationships we've been exploring. This isn't just academic pedantry, it's a direct linguistic reflection of our hard-won understanding of the system's gravitational architecture. The foundation of this system is brilliantly simple in its logic. The brightest star in the system, as seen from Earth, is given the capital letter A. Its binary companion, if it has one, becomes B. So, a simple binary system is neatly labeled as component A and component B. But what happens when we discover, as we did with Castor, that each of those components is itself a pair of stars? This is where the lowercase letters come in. The primary or brighter star of the pair that makes up component A is designated R. Its fainter, close-orbiting companion becomes AB. Similarly, the stars in the B pair become Ba and BB. This creates an immediate visual hierarchy. The capital letter denotes the wider orbital partnership, while the lowercase letter specifies the individual star within that tightest of pairs. It's a family tree written in code. When a third, wider orbit binary pair is discovered, like Castor C, the pattern continues. Its stars become Ka and CB. This convention elegantly scales to even more insane levels. If by some miracle we found a star orbiting component R in an incredibly tight orbit, it would be designated Ob, creating a triple-decker name that perfectly describes its place in the celestial pecking order. This system, while logical, can lead to some genuinely tongue-twisting results. Reciting the full roster of a sextuple system sounds less like astronomy and more like reading out a complex chemical formula or a particularly obtuse line of computer code. But the beauty of it is that the name itself becomes a map just by seeing the designation HD123456R. An astronomer immediately knows that this star is the primary member of the tightest binary pair within the wider component out of the system. They understand its relative brightness and its position in the gravitational hierarchy without needing to see a diagram. This naming scheme has proven essential for publishing research, coordinating observations across different telescopes, and building the precise computer models that untangle the system's dynamics. It transforms a seemingly random collection of stars into an ordered catalog, a testament to our human need to impose structure on even the most chaotic of natural phenomena. So the next time you see a string of letters like TYC3012BB, remember that you're not just looking at a random name, you're looking at a tiny, precise biography of a star's place in its complex family. The story of sextuple systems isn't just one of delicate balance. It's also a tale of cosmic violence so extreme it can create the fastest solo travelers in the entire galaxy. Our 18th discovery reveals that these complex families are likely breeding grounds for hypervelocity stars, lone suns rocketing through the void at speeds so great they can actually escape the gravitational pull of the Milky Way itself. To understand how this happens, we need to revisit the very cradle of these systems, the dense, chaotic environments where they are often born or reside. Picture a crowded stellar dance floor where multiple star systems swing past each other in a gravitational free-for-all. Within a sextuple system, you already have a ticking clock of orbital interactions. But if this system has a close encounter with another massive object, perhaps another star cluster or a giant molecular cloud, the stage is set for a celestial slingshot of unbelievable power. The mechanics of this ejection are a masterclass in gravitational energy transfer. Imagine a simple scenario involving 3 stars, 2 in a tight binary pair, and a third, more massive single star passing close by. As the single star swings past the binary, a complex gravitational tug of war ensues. The interloper can transfer a significant amount of its kinetic energy to one of the stars in the binary. In the most dramatic cases, this energy boost is so immense that the recipient star is accelerated to a velocity exceeding the system's escape velocity. It isn't just nudged into a wider orbit, it is hurled away like a stone from a sling, breaking all gravitational bonds with its former family. In a sextuple system, the potential for this is magnified because you have multiple pairs of stars, each with their own deep gravitational wells, acting as perfect engines for this kind of energy exchange. The incoming perturber doesn't just interact with one star, it interacts with a complex, pre-packed gravitational system primed for a violent reaction. The result can be an ejection event that propels a star outward at hundreds or even thousands of kilometers per second. But there's an even more violent ejection mechanism lurking within these systems, the supernova kick. We've discussed how the death of one star in a supernova explosion can destabilize the entire family. The key to creating a hypervelocity star lies in the asymmetry of that explosion. When a massive star goes supernova, the detonation is rarely perfectly spherical. If more of the blast erupts in one direction, the resulting recoil can kick the remaining stellar corpse, a neutron star or black hole, with tremendous force. Now consider if that exploding star was one half of a very tight binary pair. Before the explosion, the 2 stars were orbiting each other at high speed. The instant the supernova occurs, the dying star instantly loses a huge fraction of its mass. The gravitational glue holding the pair together vanishes in a flash. The surviving companion, now feeling the grip of its partner disappear, is essentially released from its orbital tether. At the same time, the supernova kick sends the neutron star flying in one direction. Due to the conservation of momentum, the companion star is flung off in the opposite direction, at a speed comparable to its original orbital velocity, plus an extra boost from the explosion's recoil. This 1-2 punch can easily launch the survivor on a trajectory that makes it a hypervelocity runaway. The hunt for these stellar cannonballs has become a major area of astronomical research. Using powerful telescopes and precise data from missions like Gaia, which maps the motion of billions of stars, astronomers have identified several dozen candidates hurtling through the galaxy at speeds well over 500 kilometers per second. By tracing their paths backward through the Milky Way, some of these hypervelocity stars appear to originate not from the galactic center, another proposed source, but from the galactic disk, the very plane where star formation and dense multiple systems are common. Finding a hypervelocity star whose backtrack path intersects with a known or even a suspected multiple star system would be a smoking gun, directly linking these incredible cosmic projectiles to the violent interactions within stellar families. These runaway stars are more than just curiosities. They are celestial fossils, their high-speed trajectories carrying the indelible imprint of the cataclysmic event that gave them their freedom, serving as permanent reminders that the beautiful order of a sextuple system is often paid for with the violent expulsion of one of its own. But what if the cosmic ballet of a sextuple system wasn't just a series of nested circles, but something far more intricate, a dance where the stages themselves are tilted at impossible angles? This brings us to a theoretical possibility that stretches the imagination, a polar configuration where the orbital planes of the different binary pairs are not just slightly misaligned, but are inclined almost perpendicular to one another. Picture our familiar hierarchical model, but now twist it. Imagine the tight binary pair at the system's heart orbits in a flat plane like a spinning coin on a table. The second binary pair, which orbits the first, does so in a plane that is tilted 90 degrees, so its path traces a vertical circle around the horizontal one, like a Ferris wheel rotating around the coin. Now introduce the third, outermost pair, whose orbital plane could be tilted at yet another extreme angle relative to the other two. The resulting celestial motion would be a gravitational labyrinth of breathtaking complexity, a three-dimensional choreography utterly unlike the relatively flat disk of our own solar system. The observational consequences of such a polar configuration would be extraordinary, particularly when it comes to the system's light curve, the graph of its brightness over time. In a typical system with roughly aligned orbits, eclipses happen with a predictable regularity. But in a polar system, the geometry of shadow becomes a chaotic art form. From our fixed viewpoint on Earth, the stars would pass in front of and behind each other on wildly different paths. One eclipse might be a deep, long-lasting event as a large star transits fully across the face of another. The next eclipse could be a brief, grazing passage where the stars only partially overlap. Because the orbits are so inclined, there would be long periods where no eclipses occur at all from our perspective, as the stars are simply moving above or below each other in our line of sight. Then, as the orbits slowly process, meaning their orientation gradually shifts over time, new eclipse sequences would suddenly begin, only to fade away again centuries later. The light curve would be a sporadic, unpredictable series of events, a cryptographic message that would take immense effort to decode, revealing the true, twisted architecture of the system. Beyond eclipses, the gravitational interactions in a polar configuration would be far more intense and chaotic. The Kozylidov mechanism, which we discussed earlier, thrives on orbital misalignment. In a system where the planes are nearly perpendicular, this effect would be supercharged, driving the eccentricities of the inner orbits to extreme maxima. This would mean that even if the average distance between stars is safe, their closest approaches could become dangerously intimate, dramatically increasing the chances for tidal stripping, mass transfer, and violent stellar collisions. The polar setup would act as a continuous gravitational stirrer, keeping the system in a state of perpetual dynamic tension. For any potential planets, the stellar sky would be a source of constant wonder and terror. Instead of the suns following a predictable path along the ecliptic, as our sun does, they would rise and set in completely different parts of the sky, following independent crisscrossing arcs. A planet might experience a sunrise in the north, followed hours later by a second sunrise in the east and a sunset in the south, creating a daylight period with no single direction of light and shadows pointing in multiple, conflicting directions. The concept of seasons would be rendered meaningless, replaced by a climate dictated by the complex and ever-changing combinations of stellar illumination and gravitational heating. While no such perfectly polar sextuple system has been confirmed, The search for these extreme architectures pushes our understanding of celestial mechanics to its absolute limit, revealing just how creatively twisted the universe's gravitational artistry can be. But the true impact of this chaotic stellar ballet on a planet goes far deeper than just its surface temperature. It strikes at the very integrity of its atmosphere. On Earth, our atmosphere is a protective shield nurtured by the steady, gentle warmth of a single sun. But for a world orbiting within a sextuple system, the atmosphere itself becomes a battlefield, constantly bombarded by a wildly fluctuating barrage of high-energy radiation from multiple sources. The primary aggressor is ultraviolet light, particularly the most energetic forms known as extreme UV and X-rays. A young hot star is a prodigious emitter of this harsh radiation, which acts like a cosmic sandblaster on planetary gases. In our solar system, planets like Mars are thought to have had their thick atmospheres slowly eroded over billions of years by the solar wind. Now amplify that threat by a factor of 6. A planet in a sextuple system would be subjected to ultraviolet radiation from several stars at once, each with its own intensity and variability. During periods when 2 or more hot, young stars are high in the sky, the combined UV flux could be intense enough to rip molecules apart in the upper atmosphere, ionizing them and giving them enough energy to achieve escape velocity, literally boiling the atmosphere away into space. The result would be atmospheric weather of an almost unimaginable scale, driven not by temperature differences alone, but by chemistry and physics occurring at the atomic level. The constant ionization would create a permanent, global electric field in the upper atmosphere, leading to planet-wide auroras that dance not just at the poles, but across the entire sky, a perpetual, silent storm of light. The chemistry would be equally bizarre. On Earth, ultraviolet light from the sun plays a crucial role in creating and destroying ozone in a delicate balance. In a multi-star environment, this balance would be shattered. Ozone layers might form and be obliterated in cycles lasting only days or years, depending on the orbital positions of the most active stars. Without a stable ozone layer, the planet's surface would be bathed in lethal doses of UV radiation during certain orbital configurations, making the emergence of life as we know it an incredible challenge. The very composition of the air could change dramatically. Methane, a potent greenhouse gas, is easily broken down by UV light. Its concentration in the atmosphere would swing wildly, causing runaway greenhouse effects that heat the planet suddenly, followed by deep freezes when the methane is depleted and the atmosphere thins. Perhaps the most fascinating possibility is the creation of a temporary hybrid atmosphere. Imagine a planet with a thick, Venus-like atmosphere of carbon dioxide. Now imagine a flare from a nearby star or the steady output from a particular stellar companion is intense enough to break apart the CO2 molecules, freeing the oxygen atoms. These atoms could then combine to form a transient layer of ozone or combine with other elements, creating entirely new compounds. The atmosphere wouldn't be a static mixture, it would be a dynamic chemical reactor, its recipe changing based on which stars are dominant in the sky at any given time. For any potential life forms, this would represent an evolutionary hurdle of astronomical proportions. Life would not only have to adapt to wildly changing temperatures and light levels, but also to a constantly shifting chemical environment where the very air it breathes could become toxic or vanish entirely on timescales that could be shorter than a single generation. This transforms the concept of a habitable zone from a simple region where liquid water can exist to a four-dimensional puzzle where time itself is a critical ingredient for survival, demanding a level of resilience we can scarcely comprehend. Amidst all this cosmic chaos, it's almost paradoxical that these same sextuple systems have become some of the most precise timekeeping instruments in the universe. Their intricate gravitational dances, when measured with the incredible accuracy of modern astronomy, transform them into what can only be described as celestial metronomes, their rhythmic orbits ticking with a stability that rivals atomic clocks. This precision turns them into unparalleled natural laboratories, allowing scientists to conduct rigorous tests of fundamental physics on a scale that would be impossible to replicate in any lab on Earth. The key lies in the clockwork predictability of their hierarchical orbits. While the overall system is complex, the individual binary pairs, especially the innermost ones, often follow orbits that are so stable and well-defined that their periods can be measured down to a fraction of a second over many years. Each completed orbit is a tick of this cosmic clock, and by observing thousands of these ticks, astronomers can detect minuscule deviations that would otherwise be invisible. This extraordinary precision makes these systems powerful probes for testing Einstein's theory of general relativity. According to the theory, massive objects in tight orbits should slowly lose energy by emitting gravitational waves, causing their orbits to decay imperceptibly over time. In our solar system, this effect is too small to measure with current technology, but in a tight binary pair within a sextuple system, where stars whirl around each other at ferocious speeds, this orbital decay can be significant enough to detect. By meticulously timing the eclipses of such a binary over decades, astronomers can see if the stars are, in fact, spiraling inward at exactly the rate predicted by Einstein. Any discrepancy between the observed orbital decay and the theoretical prediction would be a monumental discovery, potentially pointing toward new physics or a modification of our understanding of gravity itself. Furthermore, the gravitational influence of the wider stellar pairs in the system creates additional, subtle effects. The slow precession of an inner orbit, the gradual rotation of its orientation in space, can also be measured with stunning accuracy. This precession is caused by the gentle gravitational tug from the other stars, and its rate depends on their masses and distances. By measuring it, scientists can essentially weigh the distant stellar components with a precision that is difficult to achieve by any other method, providing a critical check on our models of stellar structure and evolution. Beyond testing gravity, these systems serve as long-term cosmic experiments for stellar evolution. Our theories about how stars age are built on observations of millions of stars at different stages of life, but we rarely get to watch a single star evolve in real time over millions of years. In a sextuple system, however, we have a snapshot of 6 stars that all formed from the same cloud of gas at the same time. They are a controlled experiment, born with the same initial chemical composition but with different masses. According to theory, the most massive stars should evolve the fastest, swelling into red giants or exploding as supernova before their lower mass siblings have even changed appreciably. By studying a sextuple system, astronomers can check if the stars are indeed following this script. Is the most massive component showing signs of advanced age? Are the lower mass stars still in their stable, youthful phase? Any deviation from the expected pattern is a clue that our models might be missing a crucial piece of physics, perhaps related to the tidal interactions or mass transfer that we know occur in such close quarters. The system becomes a benchmark, a Rosetta Stone for translating stellar spectra into a reliable timeline of stellar life and death. By using these cosmic clocks, we are not just learning about the stars themselves. We are calibrating the very timescales on which the universe operates, turning a chaotic family of suns into a fundamental tool for understanding the laws that govern all of reality. This relentless gravitational interplay, where stars steal material and reset their clocks, sets the stage for even more spectacular and volatile events. When the cosmic vampire at the heart of a binary pair is not just any star, but the super-dense corpse of a dead sun, the act of feeding becomes a truly cataclysmic affair. Within the complex web of a sextuple system, these compact objects, white dwarfs and neutron stars, can transform a stable stellar family into a powerful engine for some of the most energetic phenomena in the universe, nova and X-ray binaries. The process begins much like the creation of a blue straggler, with one star in a tight pair expanding and spilling its material onto its companion. But if the receiving star is a white dwarf, the entire dynamic changes. A white dwarf is not a living star with an active core. It is an incredibly dense sphere of degenerate matter, a remnant about the size of Earth but containing the mass of our Sun. When hydrogen-rich gas from its companion star flows onto the white dwarf's scorching hot surface, it doesn't gently mix in. Instead, it accumulates under the immense surface gravity, piling up into a dense, pressurized layer. For a time, this layer simply heats up, but the white dwarf's gravity is so intense that it continuously compresses the base of this hydrogen ocean. Over months, years, or even centuries, the temperature and pressure at the bottom of the layer climb to a critical threshold. When they reach around 20 million degrees, a runaway thermonuclear fusion reaction ignites. The entire amassed layer of hydrogen explodes in a sudden, violent flash, causing the white dwarf to increase in brightness by a factor of 50,000 to 100,000 in a matter of hours. This is a nova. From our perspective, a seemingly ordinary star in the Sextuple system suddenly flares into a brilliant new star, outshining its 5 siblings for a brief, spectacular period before gradually fading back to its original state. This isn't a star being destroyed, it's a surface detonation, and because the white dwarf itself survives, the process can repeat. The system can experience these nova eruptions again and again, as long as the donor star continues to supply fresh fuel. Now imagine the same scenario, but with an even more extreme compact object, a neutron star. A neutron star is the collapsed core of a massive star, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. Its gravitational pull is almost unimaginably strong. When it pulls material from a companion, the gas doesn't just fall onto the surface, it is accelerated to nearly the speed of light. As this superheated plasma spirals inward, it forms a searingly hot accretion disk around the neutron star. The friction within this disk heats the material to temperatures of millions of degrees, causing it to glow not in visible light but in high-energy X-rays. This transforms the binary pair into what astronomers call an X-ray binary, a beacon of intense radiation that can outshine the entire combined light of the other 5 stars in the system at these specific wavelengths. The energy output is staggering, a direct conversion of gravitational potential energy into some of the most penetrating light in the cosmos. In a sextuple system, the other stellar pairs are not mere spectators to this drama. Their gravitational influence can profoundly affect the accretion process. A periodic tug from a wider orbiting binary can slightly alter the neutron star's orbit, compressing it at certain times and stretching it at others. This, in turn, regulates the flow of material from the donor star, potentially turning the X-ray output on and off in a long-term cycle. The system could flicker between a quiet state and an active, high-energy one, dictated not just by the intimate dance of the neutron star and its victim, but by the grand, slow waltz of the entire stellar family. This connection elevates sextuple systems from being mere curiosities to vital natural laboratories for understanding stellar death and rebirth. Observing a nova eruption within such a complex system provides a unique opportunity. By carefully measuring the light curve and the spectra before, during, and after the explosion, astronomers can calculate exactly how much material was ejected and at what velocity. They can then compare this to models to understand the physics of nuclear burning on the surface of a white dwarf with unparalleled precision. Furthermore, because all 6 stars in the system share a common origin, we know the age and initial composition of the white dwarf's progenitor star with much greater certainty than for an isolated nova. This gives us a fixed starting point for modeling its entire life cycle, from birth to death to its current explosive behavior. For X-ray binaries, the benefits are equally profound. The presence of the other stars helps to pin down the mass of the neutron star with incredible accuracy. By observing how the neutron star's orbit is perturbed by its stellar relatives, we can measure its gravitational influence with extreme precision, which directly tells us its mass. This is crucial for understanding the equation of state of neutron star matter, the fundamental physics that governs how this ultra-dense material behaves under pressure, a question that remains one of the great frontiers in astrophysics. Therefore, the chaotic environment of a sextuple system, which might seem too turbulent for precise science, actually provides the stable, long-term gravitational framework that allows us to weigh the universe's most exotic objects and witness the aftermath of stellar death in exquisite detail. But what if a star's life is not a one-way journey from birth to death? What if, within the frantic gravitational dance of a sextuple system, a star can cheat death, reverse its aging process, and rise from its own ashes like a cosmic phoenix? This brings us to one of the most bizarre and counterintuitive discoveries, the existence of zombie stars. These are stellar anomalies that appear to defy the natural life cycle, stars that have been fundamentally altered not by internal processes, but by the actions of their companions, effectively rejuvenated to walk the galaxy again long after they should have faded away. The most common path to this stellar resurrection is through the process of mass transfer we've discussed, but the consequences are far more profound than just a change in brightness. Imagine a typical binary pair within the sextuple system. One star is more massive and has evolved faster, swelling into a red giant. Its smaller, lighter companion orbits nearby. As the giant expands, it begins to spill its outer layers onto the smaller star. This isn't just a simple donation of fuel, it's a transfer of youth. The receiving star, which was once burning its hydrogen fuel at a slow, steady pace appropriate for its mass, suddenly gains a massive influx of fresh hydrogen. This new material falls onto its surface, increasing the star's total mass. In the core of a star, mass is destiny. More mass means greater gravitational pressure, which in turn increases the core temperature and reignites hydrogen fusion with a new, ferocious intensity. The star responds by becoming hotter, bluer, and vastly more luminous. It transforms from a modest, middle-aged star into a brilliant, blue, youthful-looking powerhouse. Astronomically, it has become a blue straggler. It now appears billions of years younger than its actual age, a classic case of a zombie star shambling on with a new lease on life stolen from its companion. But the process can be even more extreme, leading to a full stellar merger. Picture two stars in a very tight orbit, their gravitational dance gradually decaying due to tidal forces or the emission of gravitational waves. They spiral closer and closer until their outer atmospheres touch. At this point, the delicate balance is broken, and the two stars plunge into each other, coalescing into a single, new object over a relatively short, violent period. The result is not a simple sum of its parts. The merger violently mixes the material from both stars, stirring hydrogen from the outer layers down into the core and bringing up helium from the interior. This creates a single star with a confused and thoroughly mixed chemical composition, a Frankenstein's monster of stellar evolution. This newborn star, born from a collision, will be more massive than either of its progenitors. It will light up with the vigor of a truly young star, but its internal chemistry is a chaotic mess that doesn't match any standard model of stellar formation. It is a zombie in the truest sense, a new entity created from the dead bodies of two older stars, its evolutionary history completely erased and rewritten in a single cataclysmic event. The presence of such a star within a sextuple system creates a profound puzzle for astronomers trying to date the system's age. The standard method for determining the age of a star cluster is to look at its color magnitude diagram, a graph that plots stars' brightness against their color. Massive, hot, blue stars burn out quickly, so if you see them in a cluster, you know the cluster must be young. but a zombie star, whether a blue straggler from mass transfer or a merger product, will sit right there among the hot blue stars, masquerading as a youthful member. If you didn't know its true nature, you would drastically underestimate the age of the entire system. In a sextuple system, this deception is compounded. You have 6 stars that you know were born at the same time, but one of them looks completely out of place. Its existence forces astronomers to become cosmic detectives, searching for the telltale clues of its unnatural origin, such as unusual chemical abundances or evidence of a rapid rotation spin imparted by the merger process. This zombie star, therefore, is not just a curiosity. It's a vital key to understanding the violent interaction history of the entire stellar family, a living testament to the fact that in the cosmos, death is not always the end, but can be a gateway to a strange and twisted new life. But if the gravitational architecture of a sextuple system seems like the pinnacle of complexity, then prepare to have your conception of cosmic limits shattered once more. The hunt for stellar multiplicities does not end at 6. Astronomers are actively searching for systems with 7, 8, or even more stars bound together in a single gravitational conspiracy. This raises a profound and tantalizing question. Just how many suns can share one cosmic address before the entire structure collapses under the weight of its own gravitational contradictions? The search for these higher multiplicities pushes observational technology to its absolute limits and forces theorists to confront the ultimate boundaries of celestial stability. The current confirmed record holder is a system known as AR Cassiopeae, a septuple system located about 1,500 light-years away. For a long time, it was classified as a complex eclipsing binary, but painstaking analysis of its light and radial velocity over decades revealed a truth far stranger. The system is now understood to consist of 7 stars arranged in an even more elaborate hierarchical dance than Castor. While the full details are still being unraveled, it appears to be a system built upon a quadruple core, 2 close binaries orbiting each other, with an additional triple system, itself a tight binary with a wider companion, orbiting the entire central group at a vast distance. Every time we think we've found the most complex possible arrangement, the universe seems to delight in presenting us with an even more intricate puzzle. Beyond septuple, the evidence becomes more speculative, but the potential exists for systems of staggering scale. There are candidate systems based on complex spectroscopic and astrometric signals that suggest the presence of 8 or even 9 gravitationally bound stars. Confirming these is a monumental challenge. The orbital periods for the widest pairs in such a system could stretch to hundreds of thousands or even millions of years, far longer than the entire history of modern astronomy. We are essentially trying to map a celestial dance by observing a single, brief twitch of one dancer's finger. The gravitational influences become so subtle and overlapping that teasing apart the signal of an 8th or 9th star from background noise or instrumental error is a task at the very frontier of data science. Furthermore, the light from these systems becomes an almost indecipherable blend. With so many stars of different temperatures and luminosities contributing, the combined spectrum is a chaotic superposition of fingerprints, and the light curve from mutual eclipses would be a continuous, unpredictable flicker with no discernible repeating pattern over human timescales. Finding these ultra-multiple systems is less like solving a puzzle and more like reconstructing an entire ancient language from a handful of fragmented inscriptions. This quest inevitably leads to a theoretical cliff edge. Is there a fundamental limit to stellar multiplicity? Physics suggests that there must be. The principle of hierarchical stability that allows sextuple and septuple systems to exist relies on a steep decline in gravitational influence with distance. Each subsequent pair added to the system must orbit at a significantly greater distance to avoid destabilizing the delicate inner balances. But this expansion cannot continue indefinitely. At some point, the gravitational bond holding the outermost star or pair to the central group becomes so weak that it is easily broken. A passing star in the galaxy, a distant encounter with a molecular cloud, or even the cumulative gravitational tugs from the rest of the galaxy over billions of years would provide more than enough energy to sever that tenuous link. The system would simply evaporate, its most distant members drifting away into the interstellar void. This theoretical maximum is not a fixed number like 7 or 9. It depends critically on the environment. A system born in an extremely dense and isolated globular cluster might be able to hold onto more members for a longer time, as the external gravitational perturbations are more uniform. A system in the busy galactic disk like our own would face a much greater risk of disruption. The search for the ultimate multiple system, therefore, is also a search for the most pristine and quiet gravitational environments in the galaxy, cosmic backwaters where such fragile architectures can endure for eons undisturbed. Contemplating these limits brings us full circle to the very nature of what defines a star system. Is our own solar system with its single sun the rule or the exception? As we discover more of these stellar families, it becomes clear that while higher multiplicities are exceedingly rare, complexity might be more common than we ever imagined. The existence of septuple and potential octuple systems suggests that the universe has no inherent preference for simplicity. If the conditions are right, a massive, spinning cloud, a dense stellar nursery, a series of fortunate gravitational captures, then nature will assemble these cosmic marvels. They stand as ultimate tests of our understanding, challenging us to refine our models of gravity, stellar evolution, and planetary formation under the most extreme conditions imaginable. Each new discovery in this field doesn't just add another star to a list. It forces us to rewrite the textbooks on celestial mechanics, reminding us that the cosmos is capable of an artistry far grander and more complex than our simplest models can predict. Now, let's take a speculative leap into one of the most profound and mysterious questions in all of modern cosmology. We've explored how the complex motions of stars within a sextuple system are governed by the visible gravitational pull of their siblings. But what if there's another, invisible player in this celestial dance? This brings us to a fascinating and highly speculative idea. Could the gravitational dynamics of the widest sextuple systems be subtly influenced by dark matter? We know that dark matter, this mysterious substance that does not emit or absorb light, makes up about 85% of the matter in the universe. Its presence is inferred from its gravitational effects on the largest scales, like the rotation speeds of entire galaxies and the bending of light from distant objects. But what about on the scale of a single star system? The conventional view is that dark matter is spread out in a vast, diffuse halo surrounding galaxies, and its density within a solar system would be so low that its gravitational pull would be utterly negligible compared to that of the suns and planets. It's like trying to detect the weight of a single dust grain added to a freight train. However, some theoretical models suggest that dark matter might not be perfectly smooth. It could clump together, forming what are known as dark matter substructures or microhalos. If such a clump, even a relatively small one, were to pass through or linger near a widely separated sextuple system, its additional gravitational mass could have a detectable effect. Think of the system's intricate orbital clockwork. The paths of the stars, especially the outermost pairs whose gravitational bonds are already tenuous, are calculated with incredible precision based on the known masses of the visible stars. If their observed motions show tiny, persistent deviations from these predictions, a slight wobble or an inexplicable acceleration that can't be accounted for by any known object, it could point to the gravitational influence of unseen mass. In other words, the precise orbits of the stars could act as exquisitely sensitive scales, weighing the presence of dark matter in their immediate vicinity. A sextuple system with its multiple, long-period orbits acting as independent gravitational probes would be a perfect natural laboratory for this kind of investigation. Each binary pair, with its unique orbital period and orientation, would sample the gravitational field along a different path, allowing astronomers to triangulate the position and approximate mass of any invisible perturber. This idea transforms these stellar families from being subjects of study in their own right into potential tools for probing the fundamental nature of the universe. Confirming such an effect would be monumentally challenging. The deviations would be minuscule, requiring decades, perhaps centuries, of ultra-precise astrometric measurements from space-based observatories even more advanced than Gaia. Scientists would have to rule out every other possible explanation, such as the gravitational pull of a hidden, very low-mass brown dwarf or a rogue planet drifting through the system. But if all conventional explanations were exhausted, the tantalizing possibility would remain that we are witnessing the fingerprint of dark matter on a stellar scale. It would mean that dark matter can be concentrated enough to influence the dynamics of individual solar systems, opening up a completely new window into its properties. We could move from simply knowing dark matter exists to understanding how it clusters, how it interacts with itself, and how it is distributed on scales far smaller than ever before possible. While firmly in the realm of speculation today, this concept highlights the incredible potential of using the universe's most complex structures as natural instruments to illuminate its deepest secrets. Now, let your imagination soar to the surface of a world that has not one but 6 suns. This is not a scene from science fiction, but a breathtaking possibility born from the gravitational stability we've explored. From the vantage point of a hypothetical planet orbiting safely within the system's broad habitable zone, the sky would be a canvas of unparalleled celestial artistry. The first thing you would notice is the light itself. It would not be the simple, singular white-yellow of our sun, but a rich, blended glow, a tapestry woven from the distinct hues of its multiple stellar parents. Imagine a dominant, brilliant white sun, similar to our own, sharing the heavens with a slightly smaller orange companion. Their combined light would cast shadows with soft, fuzzy edges, a permanent state of double illumination. But that's just the beginning. Adding to the palette might be the deep crimson glow of a distant red dwarf, a constant ruby ember in the sky, and the fierce, actinic blue point of a hot, massive star. The overall quality of daylight would be strange and beautiful, a blend of warm and cool tones that would make colors on the landscape appear subtly different, shifting throughout the long and complex day. The concept of a day itself would be rendered meaningless in any familiar sense. With 6 stars in a complex hierarchical dance, their risings and settings would follow an intricate, multi-layered clock. There would be periods of single daylight, double daylight, or even triple daylight as different combinations of suns crest the horizon. The suns would not follow a single path like our ecliptic. Their orbits, likely inclined at different angles, would see them tracing independent, crisscrossing arcs across the sky. One sun might rise in the east, climb high, and then be joined hours later by a second sun rising in the north, their light blending to create a dazzling, multi-directional illumination where shadows point in several directions at once. That nights would be a relative term. True darkness might be a rare event, occurring only when all 6 suns are briefly below the horizon. More often, the sky would be bathed in a perpetual twilight or a soft, multicolored glow from the various suns that remain above the horizon or are just below it, creating a permanent, beautiful aurora-like illumination. The most spectacular events would be the eclipses, but these would be phenomena of a scale and complexity we can scarcely conceive. Instead of our moon passing in front of the sun, you might witness a large, cool, orange giant slowly drifting in front of a smaller, hotter blue star. The quality of light would shift dramatically, cooling from a sharp blue-white to a deep, somber orange, and the shadows would change in both intensity and color. Even more mind-bending would be a double or triple eclipse, where the alignments are just right for two stars to occult a third simultaneously from the planet's viewpoint. The sky would dim in steps, a series of layered shadows falling over the world. At other times, one star might pass behind another, its light flaring into a brilliant ring as it is lensed by the gravity of the closer star. The eclipses would not be predictably periodic like our own. Their patterns would be a chaotic symphony, with some sequences repeating over years and others over centuries, making each event a unique and awe-inspiring celestial performance. The sheer scale of the celestial motions would be humbling. The closest binary pairs would complete their frantic dance in a matter of days, their two suns visibly orbiting each other, weaving around a common center of gravity in the sky. The intermediate pairs would take years to complete a single loop, their relative positions slowly shifting season by season, and the outermost stellar partners would be like distant, barely moving beacons, their orbital period spanning millennia. An observer on this world would be living inside a three-dimensional orrery, a working model of celestial mechanics on a grand scale. The constellations formed by these six suns would be dynamic and ever-changing, reconfiguring over a single lifetime in ways our own fixed star patterns do not over thousands of years. This breathtaking vista is more than just a visual spectacle. It is a direct, visceral experience of the complex gravitational ballet that defines the system. It represents the ultimate reward for surviving the gravitational chaos, a front-row seat to the most magnificent and constantly evolving sky in the entire galaxy. Just when you think the gravitational dynamics of a sextuple system have reached their pinnacle of complexity, the universe reveals another layer of exquisite order hidden within the apparent chaos. This brings us to a phenomenon that acts as a celestial metronome, synchronizing the orbits of the stars in a way that is both mathematically beautiful and dynamically powerful: mean motion resonance. At its heart, resonance is a concept we encounter in everyday life. Think of a child on a swing. To push them higher, you don't push randomly. You time your pushes to coincide with the natural rhythm of the swing's arc. Each push adds a tiny bit of energy at just the right moment, amplifying the motion. In a sextuple star system, a similar principle of perfect timing applies, but on a cosmic scale, with gravity itself providing the push. A mean motion resonance occurs when the orbital periods of two celestial bodies form a simple integer ratio. For example, imagine that one binary pair in our system, pair A, takes exactly 100 days to complete one orbit around the system's center of mass. Now imagine a second, more distant binary pair, pair B, takes precisely 200 days to complete its own wider orbit. Their periods are in a 2-to-1 resonance. This means that for every single orbit pair B makes, pair A completes exactly 2. At regular, predictable intervals, the two pairs find themselves in the same relative configuration, with a gravitational pull between them repeating in an identical pattern. This periodic reinforcement is the key. Instead of their gravitational interactions being a random, chaotic noise, they become a rhythmic drumbeat. In many cases, this rhythmic interaction can actually enhance the system's stability. The resonating gravitational tugs can effectively lock the orbits into a protective configuration, preventing them from drifting into more chaotic, unstable arrangements. It's as if the stars have found a harmonious frequency at which to dance, their motions synchronized in a way that protects them from stumbling over each other. However, this gravitational harmony has a dark side. A resonance is not inherently stabilizing, it is inherently amplifying. Whether it leads to stability or destruction depends entirely on the specific geometry of the system. A resonance can act like a feedback loop. If the orbits are aligned in just the right way, the repeated gravitational kicks can pump energy into them, making the orbits more eccentric over time. Picture our two binary pairs again. If every time they align, the gravitational tug from pair B gives pair A a slight pull at exactly the point in its orbit that stretches it further, that small effect will compound over thousands of cycles. The orbit of Pera will gradually become more and more elliptical, transforming from a safe, circular path into a stretched-out ellipse that brings the stars dangerously close at their point of periastron. This increased eccentricity dramatically raises the risk of tidal interactions, mass transfer, or even stellar collisions. What began as a beautiful mathematical symmetry can, under the wrong conditions, become a slow-acting mechanism for gravitational suicide. The detection of these resonances in a sextuple system is a task of immense patience and precision. It requires decades, if not centuries, of precise observations to measure the orbital periods of the different pairs with enough accuracy to confirm they are in an exact integer ratio. Astronomers must meticulously time the eclipses of each binary and track their subtle wobbles through space. When they find a candidate system, they feed the data into sophisticated N-body simulations to see if the proposed resonant configuration can indeed persist for billions of years, or if it is a transient state on the road to instability. The presence of a resonance also provides a powerful tool for weighing the system, because the specific resonant frequencies depend on the masses of the stars involved. Confirming a 2-to-1 or 3-to-2 resonance allows astronomers to calculate the masses of the stellar components with extraordinary precision, providing a crucial check on models of stellar evolution. The existence of mean motion resonance in these extreme environments is a stunning demonstration that even within the most complex gravitational systems, the universe has a tendency to find patterns, to fall into rhythms, and to obey mathematical relationships that turn chaotic motion into a form of cosmic music, a harmony of spheres whose notes can either create enduring order or sow the seed of eventual destruction. While our own solar system features a relatively placid asteroid belt between Mars and Jupiter, a region of orderly orbits where leftover planetary building blocks circle the Sun, this quiet arrangement would be an impossible dream within the gravitational storm of a sextuple system. The fate of any asteroid belt in such an environment is one of relentless chaos, a discovery that helps explain some of the most puzzling observations in all of astronomy: the mysterious clouds of warm, infrared-emitting dust found around many mature stars. In our system, the asteroid belt is a stable relic of the protoplanetary disk, its inhabitants shepherded by Jupiter's gravity into orbits that avoid frequent destructive collisions. But place that same nascent belt inside a family of 6 suns, and the concept of a shepherd becomes a cruel joke. The gravitational tides from multiple stars, each on a different orbital path and timescale, would act as a constant and unpredictable source of perturbation. Instead of gentle nudges that maintain order, the asteroids would receive violent gravitational shoves from all directions, sending their orbits into a state of permanent frenzy. The result would be a demolition derby of cosmic proportions. In this chaotic environment, the asteroids would not glide past each other in stable, predictable paths. Instead, they would be forced into wildly eccentric and intersecting orbits, guaranteeing that collisions are not a rare occurrence but a constant and violent reality. These would not be the gentle, low-speed impacts that can sometimes cause asteroids to stick together and grow. They would be high-velocity smash-ups, occurring at speeds so great that the colliding bodies don't coalesce, they vaporize. Each catastrophic impact would shatter the asteroids into a finer and finer cloud of dust, a perpetual grinding process that turns a potential belt of solid worlds into a diffuse, glowing shroud of silicate and carbon grain. This dust is then heated by the intense light from the multiple stars, causing it to radiate copious amounts of infrared light. For astronomers, this is the telltale signature. When a star system shows an unexpected excess of infrared radiation, it often points to the presence of such a warm dust cloud, a silent witness to an ongoing, unseen cataclysm. This discovery provides a brilliant solution to a long-standing mystery. For decades, telescopes have detected this excess infrared glow around stars that are billions of years old stars like our Sun, which should have long ago cleared their neighborhoods of this primordial dust. In a single star system, the dust from the original planet-forming disk should either have clumped together into planets or been blown away by stellar radiation within a few 100 million years. Its persistent presence around older stars was perplexing. The existence of sextuple and other complex multiple systems offers a compelling explanation. In these gravitational maelstroms, the process of grinding down asteroids into dust is not a one-time event from the system's youth. It is a continuous, self-sustaining cycle that can last for the entire lifetime of the stars. As long as there are moon-sized planetesimals left to perturb, the gravitational forces will ensure they eventually cross paths and pulverize each other, constantly replenishing the dust supply. The observed infrared excess around some stars may therefore be the direct fingerprint of a hidden, complex stellar family, a sign that what looks like a single point of light is actually a cosmic battlefield where asteroids are eternally being sacrificed to the relentless dynamics of gravity. But what if we could move beyond these mathematical models and blurred points of light to actually see these stellar families in crisp, breathtaking detail? For centuries, studying sextuple systems has been an exercise in indirect detective work, interpreting flickers and spectral wobbles. But a new era of observation is dawning, one that promises to transform these cosmic mysteries into high-definition portraits. The next generation of telescopes, led by the James Webb Space Telescope and the ground-based Extremely Large Telescope, are not just incremental improvements. They are quantum leaps in capability that will allow us to witness the intricate dance of these systems as never before. The James Webb Space Telescope, with its colossal gold-coated mirror and suite of infrared instruments, is uniquely suited to attack one of the fundamental challenges of observing sextuple systems: contrast and resolution. Many of the stellar components, particularly the smaller, cooler red dwarfs and any potential white dwarfs, are incredibly faint compared to their brilliant siblings. In visible light, their signal is simply washed out, lost in the glare. But Webb sees the universe in infrared light where these cooler stars shine most brightly. This dramatically reduces the contrast problem, allowing Webb to pick out the faint embers huddled near the stellar infernos. Furthermore, Webb's location at the stable Lagrange point 2, far from the distorting effects of Earth's atmosphere, combined with its advanced coronagraphs, masks that block the light of bright stars, will enable it to directly image components that have until now been only theoretical shadows in our data. We will no longer have to infer the existence of Castor C and its binary nature. We will see it as a distinct, separate pinprick of light, measuring its brightness and color directly. This alone will provide massive constraints for our models, giving us precise temperatures and luminosities for every member of the family. Yet, the revolution goes even deeper than mere imaging. Webb's powerful spectrographs can dissect the infrared light from each individual component once they are resolved. Imagine pointing Webb at a tight binary pair within a sextuple system and being able to obtain a clean, uncontaminated spectrum for each star separately. This would end the centuries-old struggle of spectral disentanglement. We could directly read the chemical composition, measure the atmospheric pressure, and detect the presence of powerful magnetic fields on each star. For the first time, we could look for the chemical fingerprints of past mass transfer events directly on the surface of a blue straggler, confirming the vampiric history we've only been able to model. We could study the accretion disks around young stellar objects in these chaotic environments, watching in real time how the gravitational tides from sibling stars affect the earliest stages of planet formation. Webb turns these systems from blurred puzzles into a collection of individual, knowable suns. While Webb orbits in the cold of space, a behemoth is rising from the high desert of Chile. The Extremely Large Telescope, or ELT, with its 39-meter primary mirror, a colossus that gathers more light than all of the existing large optical telescopes combined, will bring a different kind of power to the problem: sheer, unimaginable resolution. The ELT's primary mission is to see with exquisite detail, exploiting a technique called adaptive optics to cancel out the blurring caused by Earth's atmosphere in real time. For sextuple systems, this means something extraordinary. It will allow us to map the orbits of the stars directly. Whereas today we track their motions through indirect wobbles, the ELT will actually watch them move. Over a period of just a few years, we will be able to create a time-lapse movie of the stars in a system like Castor, tracing the elegant ellipses of their paths around each other. This will provide the most direct and precise measurements of their masses ever obtained, putting our theories of gravity and orbital dynamics to the ultimate test. The combined power of these observatories will open a window into the possibility of life in these extreme environments. The holy grail of exoplanet science is the characterization of atmospheres, looking for signs of water vapor, oxygen, methane, and other potential biosignatures. In a sextuple system, this was previously considered an impossible dream due to the overwhelming and variable light from the host stars, but JWST and the ELT are designed for this challenge. By observing the system in infrared light where the stars are relatively dimmer and the planets are brighter, and by using the ELT's incredible resolution to spatially separate a planet from its stellar parents, we might just be able to capture the faint whisper of light that has passed through a distant world's air. If a planet exists in the habitable zone of one of these systems, we could analyze its atmosphere during a transit, not in front of a single star, but as it passes through the complex light of its multiple suns. The resulting transmission spectrum would be a record of how that atmosphere interacts with a blended spectrum of different stellar types, a chemical reaction to a unique cocktail of radiation. Finding evidence of a stable atmosphere, perhaps even one with signs of biological activity, in such a chaotic environment would fundamentally reshape our understanding of where life can take root, proving that life's tenacity might extend to the most spectacular and demanding neighborhoods in the galaxy. And so we reach the 30th and perhaps most humbling discovery of all, one that forces us to turn the telescope around, so to speak, and point it back at ourselves. After this journey through the chaotic ballet of six suns, we are left with a profound and unsettling question. In a universe dominated by complex stellar families, is our own solitary sun the true cosmic anomaly? For centuries, we have gazed at the night sky from our quiet, single-star system and assumed it represented the galactic standard. Our myths, our science, even our science fiction, have been built upon the foundation of one sun rising and setting in a predictable rhythm. But the data from modern astronomy paints a very different picture. While exact numbers are still being refined, surveys suggest that perhaps as many as 2/3 of all star systems in the Milky Way contain two or more stars. When you consider that single-star systems like our own are outnumbered by binaries, triples, and even more complex arrangements, a startling conclusion emerges. Our peaceful, orderly solar system, far from being the rule, may in fact be the exception, a quiet suburban neighborhood in a metropolis of bustling stellar cities. This realization completely upends our perspective on planetary normacy. Our entire understanding of how planets form and evolve has been sculpted by the one example we know intimately, our own. We have defined the habitable zone as a precise, shell-like region around a single star where liquid water can exist. We model climate based on the steady input of energy from one source. But if multiple star systems are the galactic standard, then our models are based on a rarity. The true norm for planets, if they can exist in such environments, would be conditions of extraordinary variety and dynamism. A planet might orbit a single star within a tight binary pair, experiencing double sunrises and complex eclipses. or it might orbit the entire system's center of mass, bathed in the blended light of several suns with days and nights of unpredictable length. The very factors we consider essential for life, a stable climate, a consistent day-night cycle, a predictable energy source, might not be universal requirements, but rather the peculiar privileges of a planet born into an unusually quiet and simple stellar family. This shift in viewpoint has dramatic implications for the search for extraterrestrial life. For decades, the hunt for Earth-like worlds has consciously or unconsciously favored planets around single, sun-like stars, filtering out the more complex systems as too chaotic. But if complexity is the norm, then we may have been ignoring the vast majority of potential real estate for life in the galaxy. Life, if it is as tenacious as we suspect, may have found ways to adapt to skies with multiple suns. It might flourish on worlds with highly elliptical orbits that experience extreme seasons, hibernating during long, cold spells and blooming during brief, intense summers. It might exist deep underground on planets subjected to intense stellar radiation, or in the oceans of moons heated by tidal forces from a gravitational dance we are only beginning to comprehend. By focusing our search on twins of our own solar system, we may have been looking for life that looks like us, in places that look like home, while the galaxy teems with possibilities far stranger and more wonderful. Ultimately, the study of sextuple star systems does more than just add to our catalog of cosmic wonders. It provides a crucial lesson in cosmic humility. It reminds us that our perspective is inherently limited, shaped by the single day to point of our own existence. What we see as the calm, natural order of the universe is, in the grand scheme of things, a quiet backwater. The chaos, the gravitational storms, the stellar vampirism, and the intricate clocks of these multiple systems, that is the true character of the galaxy. Our sun's solitude has granted us the stability necessary to ask these profound questions, to develop the science that allows us to understand our own oddity. In a universe of stellar families, we are the quiet child with a unique story. And as we continue to explore, each new discovery about these complex systems not only reveals the universe's magnificent creativity, but also helps us better appreciate the rare and precious simplicity of our own celestial home. And so, our journey through the secrets of 6 suns draws to a close, leaving us not with simple answers, but with a far deeper appreciation for the universe's boundless creativity. The overarching theme that emerges from these 30 discoveries is a beautiful paradox that within the most extreme gravitational chaos, a delicate and enduring stability can be forged. It is a stability born not of simplicity, but of an exquisite hierarchical architecture, a cosmic dance where intricate clockwork emerges from what should be pure turmoil. These systems stand as monumental achievements of celestial engineering, proving that the laws of physics contain loopholes for complexity that we are only beginning to understand. They are not celestial freak shows, they are fundamental tests of our knowledge, extreme laboratories where theories of gravity, stellar evolution, and planetary formation are pushed to their absolute breaking points. From the stellar vampirism that creates zombie stars to the gravitational time bombs of the Kozylidov mechanism, we have seen that the interactions within these families are anything but gentle. They are crucibles of cosmic violence where stars are torn apart, reborn, and launched across the galaxy as hypervelocity runaways. Yet, against all odds, this very turmoil may carve out pockets of possibility, stable orbits where a planet could exist, its sky a forever changing tapestry of light and shadow. The potential for life in such an environment forces us to expand our imagination, to consider that biology's tenacity might thrive under conditions we once thought were purely destructive. Our own quiet solar system, it turns out, may be the true cosmic outlier, a serene backwater in a galaxy where bustling stellar families are the norm. Despite all we have learned, profound mysteries remain. We still do not know for certain if these systems are born from the monolithic collapse of a single cloud or assembled piece by piece through gravitational captures in crowded star clusters. The search for polar configurations and even more complex systems of 7 or 8 stars continues to challenge our observational limits, and the tantalizing possibility that these systems could one day reveal the subtle gravitational fingerprints of dark matter reminds us that the greatest discoveries often lie just beyond the edge of our current vision. Sextuple star systems are gifts that keep on giving, each answered question giving rise to new, more fascinating puzzles. So, the next time you find yourself under a clear night sky, look up at the familiar patterns of the constellations. Remember that what appears as a single, steady point of light might be hiding an entire family of suns, locked in a dance of breathtaking complexity that has endured for billions of years. Let that sight fill you with a sense of wonder for the hidden architecture of the cosmos. We want to hear which of these strange discoveries captivated your imagination the most. Was it the idea of a planet with 6 suns, the cosmic vampire stars that steal youth, or the sheer gravitational ingenuity that holds it all together? Share your thoughts in the comments below, and as always, thank you for joining us on this exploration of the universe's most magnificent